hear me okay? So last time we were talking about functionals, in particular positive linear functionals. And what was a positive linear functional? Well, it's just a linear map from our C-star algebra A into the complex numbers. And it should send the positive elements in the C-star algebra to positive real numbers. Okay, so a couple of facts that we saw last time that are relatively important. We saw that a positive linear functional is automatically bounded. And so positivity is enough, again, like we saw for star homomorphisms, to guarantee continuity. And also, it satisfies this Cauchy-Schwarz inequality, which will come in useful later on today. So that just says that if we have phi a star b and take the absolute value of that squared, this is always bounded above by phi of a star a and phi of b star b. And of course, we know that this here is always a positive element because it's a positive linear functional, and a star a and b star b are positive elements in the C-star algebra. All right. Oh, my computer's about to fall off the desk there. That's not good. So, proposition. That A be a C-star algebra and U lambda an approximate unit, and in this case, we do want it to be, in fact, an increasing approximate unit. So sometimes I will only say approximate unit, and I usually mean it to be increasing unless I say otherwise, but I'll just state it here anyway. So if we take any continuous linear functional, so I'll denote the set of continuous linear functionals by A star, the dual. So that's just this set here. So phi is continuous and linear. Then phi is positive. Whoa, no, that's not good. If and only if the limit of phi u lambda is equal to the norm of phi. So in particular, if A happens to be unital, then of course, 1 itself is an approximate unit. So we get that phi of 1a is exactly the norm of our functional. Okay. So proof. Okay, so we have an if and only if statement. Let's start by assuming that our functional is positive, and we want to show that the norm is given by this this limit here. So we know that our approximate unit consists of positive elements and is increasing. Then the corresponding sequence we get in the complex numbers, well, this is an increasing sequence of positive real numbers. Moreover, our approximate unit is bounded. So recall these are all in the unit ball of our C-star algebra. So this means that the sequence converges to some positive real number. Okay. We also know that our elements u lambda will have norm at most 1, which means that this will be bounded by the norm. Since recall, this norm is nothing but the supremum of all of these absolute values with x at most 1. So this tells us that R is bounded by the norm of phi. Okay, so now suppose A is a positive element, norm at most 1. And we can do a few calculations here. So first of all, we have that phi of A u lambda squared using the Cauchy-Schwarz inequality is at most phi A star A. Well, I guess if A is positive, we don't really need the star there. So let's get rid of that. And u lambda is also positive, so we get phi u lambda squared. And this is less than phi A squared phi u lambda, because u lambda is smaller than u lambda squared, which was bounded by R. Okay, so what does our, oops. This is an approximate unit, so A u lambda converges to A. which means that we get that in fact 5a squared is at most r phi a squared, and a we assumed was at most 1, so we get r times the norm of phi here. Okay, so this gives us that. So recall from here we had that 5 mu, of course, is less than and what was r? This was just the limit as we wanted it to be. So that's what we were trying to show, that it's that. So that's one direction. So now we want to show that if this condition on the norm is true, if it's realized by this approximate unit, then in fact our continuous linear functional is in fact positive. So assume we have some functional and it satisfies its norm is given by this limit. Okay, so we want to show that this is positive. Let's first show that if we have a self-adjoint element, then it lands in the real numbers after applying phi. Okay, so we know at least it's a complex number, so there are two real numbers, alpha, beta, such that phi of a is alpha plus I beta. And rescaling, if we want, let's just assume that beta is greater than 0. And let's also make sure that alpha is at most, sorry, A itself has norm at most 1. So this is an approximate unit. For any n and m, we can find some lambda so that for all lambdas further along in our net, we have that a u lambda minus u lambda a is at most 1 over n. So remember, both of these things are converging to a itself. So that's a reasonable statement to make. Okay, and then we can calculate. So what does this give us? And u lambda plus IA. This is just the C-star equality. Because we assumed A was positive. And we know that u lambda is positive. Okay, so expanding that out, we get And then we use our favorite triangle inequality to get that. So we're going to break this up into 3 chunks here. We know that u lambda has norm at most 1. So this first thing is going to be at most n squared. Now, by assumption, u lambda is sufficiently large so that this is 1 over n, which means that this second hunk here will just be at most 1. And then since a was assumed to be smaller than 1, then the norm of a squared is going to be less than the norm of a itself, which in turn is less than 1. So we get that this is at most n squared plus 2. Okay, now let's look at what's happening when we're applying our, functional here. So it's linear. That's a obvious line there. And now remember that phi of a was equal to alpha plus I beta. So we can sub that in. And we're going to get minus I alpha minus I times I is plus 1 beta squared. And now alpha and beta are actually real. So this just is phi of nu lambda plus beta minus I alpha. So we get, taking the limit, this is going to be okay, so this should be 2 n phi beta. The I alphas should cancel out. We get a beta squared and then an alpha squared. Okay, so this is equal to this limit here. And we saw that, okay, so let me rephrase this slightly. This is equal to the limit that we started with. So that's going to be at most the norm of phi squared, taking the limit, times the norm of nu lambda minus a, which we saw was at most n squared plus 2. Okay, but now we have that this is less than this, and the n we picked was completely arbitrary. So we can certainly pick n to be large enough that it is bigger than, what do we want here? Bigger than, okay, so choose, if n is, let's see. So we had assumed that beta was positive, so we can certainly find an n that satisfies this. And this means for all n greater than n, we get that this here is less than n squared, phi squared plus 2n. And beta, which is certainly less than this number here. Oops. And of course, that's impossible. So by the way, this should actually be not a less than or equal, but a strictly less than. So beta could not have been positive. And this shows that phi of A is actually in R. Oops. So we're almost there. We have A and A plus. And let's assume it has norm at most 1. We can always do that by scaling. Then we have that u lambda minus A. Well, that's definitely self-adjoint. And we also have that u lambda minus A is less than u lambda. So we know that this limit here, this goes to the norm of phi, and now we're going to subtract something that's real. So we get that this is at most, sorry, that was a stupid thing to say. This is less than the norm of phi because this number is, this element in A has norm at most 1. Okay, but now taking the limit on this side, this actually gives us that this is less than phi, which means that phi of A had to be greater than 0. Okay, so now we have this nice criterion for when a linear functional is in fact a positive linear functional. This will come in quite handy, especially in the unital case when all we need to do is check that the phi of 1 is equal to the norm. Okay, so we get a nice corollary, which is to say that whenever we have a non-unital C-star algebra, then any positive linear functional has unique extension to the unitization. So phi tilde, A tilde to C, A tilde denoting the unitization. And most notably, preserves the norm. Okay, so sort of proof's not so hard. I'll let you fill in some of the details. If we have our phi, then recall that A tilde is just A plus C as a vector space, and this is a linear functional. So we can define it phi tilde of A is just going to be phi of A for every A in A. And I guess we can all guess what we will get for phi of lambda. For lambda and C. Well, let's just make that lambda times the norm of phi. Okay, clearly this is linear because we've just defined it on the two linear generators of our C-star algebra, and satisfies the norm condition uniqueness is also clear because we really didn't have any choices here to make this work. And it's positive since phi tilde is exactly phi of 1. So the next obvious question to ask ourselves is, what about more general C-star algebras and their subalgebras? Do we get a way of extending? And the answer is indeed we do. And in the case of a hereditary subalgebra, we even get a uniqueness of extension, which is another reason why hereditary C-star subalgebras are quite important. So every positive linear functional from B extends to a positive linear functional. On all of A. And if B happens to be hereditary, then phi tilde is unique and satisfies the following. So we can even say exactly what it looks like. If we take phi tilde A, then it's going to be the limit where u lambda here is an approximate unit for B. Okay, so by the previous result, without loss of generality, we might as well assume that A is unital and that B is also unital, by which I mean it contains the unit of A. And by the Hahn-Banach theorem, we know there at least exists extension of functionals. And the main thing is just to check that this thing will be positive. Well, why is it going to be positive? Well, if it's extending, if it has the same norm as phi, we know that that's just phi of the unit of B, which happens to be the unit of A. So that means, oops, this is phi tilde 1A, which implies that phi tilde is positive. Now, if B is hereditary, and this is an approximate unit for B, then this is equal to the norm of phi, which is the norm of our phi tilde, which is phi tilde of 1A, or perhaps A tilde if it wasn't unital to begin with. Which means that this limit goes to 0, and hence so we can break this up. This is going to be A minus A u lambda plus lambda A u lambda, and then we can do the triangle inequality to get this. And now we can use the Cauchy-Schwarz. Guess that should be properly squared here. Oops. Can I squeeze this in? Let's see. Okay, we just saw that these two terms here will go to 0. So this goes to 0, which is exactly what we wanted to show. So I guess I should also make sure that it's clear why this is actually in B for every A and A, I hope. And that's because this is a hereditary subalgebra. So for any positive element A, this will always be smaller. For any positive element A, since this is hereditary, this guy will be in B, and of course we can always write things as the sum of positive elements. Okay, so recall that maybe before I write this, just remember that a special type of linear functional was a state. So that was these were positive linear functionals with norm 1. And what we're building up to is a result that shows that any C-star algebra can always be represented as C-star algebra bounded operators on a Hilbert space. And we will make these Hilbert spaces out of linear functionals, or states rather. But to do this, we need to know that there are enough states, and this is what this next proposition is going to tell us. So take yourself a normal element in a non-zero C-star algebra. So recall this is something that commutes with its adjoint. Then we can always find a state such that phi of A is just the norm of A. Okay, since A is normal, the C-star subalgebra generated by A and 1A in the unitization is commutative. And then if you think back to, I don't know, maybe it was the second or third lecture, we can always find element A hat B and a phi sorry, they're throwing junk off the roof of my building. In the character space of B, such that and since phi is a character, it's multiplicative, which means that phi of 1A is 1. So we have a positive extension. So in particular, phi is positive, and therefore there's a positive extension to all of A. And we can see that phi satisfies the requirements of the proposition, phi tilde rather. Okay, so now we come to one of the most fundamental results in C-star algebra, basic C-star algebra theory, and that is the GNS construction, Gelfand-Naimark-Segal construction, which will allow us to construct representations from linear functionals and hence give us this result that every abstract C-star algebra, excuse me, is in fact concrete. Up to isomorphism. Excuse me. So what is a star representation? So properly, I guess it should be a star representation, but I'll often just call it a representation. Apologies in advance. I warn you here of a C-star algebra A. This is a pair H and pi, where H is some Hilbert space and pi, this should be a star homomorphism from A to B of H. And we say that pi is faithful if, sorry, we see that pi H is faithful if the star homomorphism here is injective. So then the observation is that if A admits a faithful representation, then it's star isomorphic to a concrete C-star algebra. So recall that a concrete C-star algebra was just any closed subalgebra of B of H. Closed under the star, of course, as well. Okay, so let's construct some representations. So take positive linear functional on your C-star algebra, and then we can define this subset of A to be all those elements A such that 5A star A is sent to 0. And this is a closed left ideal. In A, and we can define an inner product from A mod and phi so the inner product of two elements in A mod n phi, this is going to be phi of A star B. This defines an inner product. So here, inner products will be linear in the second variable. Okay, so we have two things we need to show. First of all, that this n phi here is a closed left ideal, and then that this formula here does indeed define an inner product on A mod n phi. So we need to show that B, okay, left ideal, Karen. This should be B times A is also in n phi. Okay, so B star B, that's a nice positive element. Let's divide by its norm if it's non-zero, which we might as well assume it to be. Then this is a positive element less than 1A tilde. So we can multiply on either side with A star, and that is less than A star 1 A tilde A, which is just A star A. So this implies that phi of so that's just this inside phi now. Well, that's going to be less than phi of A star A, which is 0. But of course, we see that this is the positive element, so that's a least 0, which means that and then, of course, we can just take this scalar out and get that which implies that BA is indeed in N phi. Okay, the fact that it's closed under addition. Sorry. Yeah, okay. Closure under addition, that's clear. And the fact that it's closed with respect to the norm of A follows from the fact that phi is a positive linear functional and hence is bounded. Okay, so next we want to see that this defines an inner product. So you have to remember what that means, and maybe it's a long time since you did linear algebra. So I know what is for me. So what do we need to show? We need to show that it's linear in the second coordinate. So we can take the lambda out and separate this y and z. We want it to satisfy x, z bar is the same as swapping things in the coordinates. And then we want it to be positive definite. So we want that x is always greater than 0 for every x in A and phi, and that if it is 0, then x was 0. And this should be for all x, y, z in A and phi, and every lambda in C. So we can do the calculation, get n plus n phi lambda b plus n phi plus c plus n phi. Well, by definition, that's going to be phi of A star times lambda b plus c. So of course we can move those guys in together. And this is a linear functional, so we get that this is 5 A star b plus phi of A star c. which is just what we want. So now 2 was showing that if we flip the coordinates, we take the complex conjugate here. So 5a star b we can rewrite as b star a star. And since phi is positive, this is just going to be which is precisely what we wanted. And 3, well, the first part is clear. Since phi is positive, we get that a plus n phi, a plus n phi. This is by definition phi of a star a, and that's always greater than or equal to 0. And if we happen to have that this is equal to 0, then of course a has got to be by definition in n phi. So a plus n phi itself is 0. So it indeed is positive definite. So this is not quite a Hilbert space, of course, because it's not closed, but we can now, knowing that this is an inner product, just take the closure with respect to the norm that this guy induces. So we'll denote that Hilbert space by H phi. And then for any element a and a, we can define a linear operator on a mod n phi as follows. This will just be multiplication by a. And this turns out to be linear and bounded, and so extends to an operator on this Hilbert space completion. Which I'll also actually just denote by pi phi of a. And then we actually get a star representation given by the following. So H phi is just this Hilbert space completion, and pi phi is the obvious thing. So we take A, B of H phi, and we send A to this bounded linear operator pi phi of A. This is a star representation. Okay, so pi A is defined by multiplying by A, and clearly multiplication will be linear, so it's clear that this is linear on A mod n phi. So the main thing is showing that in fact it's bounded. So we want to find out what its norm should be. Let's take an element B plus n phi with norm at most 1. So that's with respect to the norm induced by this inner product. Which it just means this, this inner product here. So of course the norm would be the square root of this, but if it's less than 1, then this would be less than 1 as well. This is 5b star b. So that's just by definition of pi. And this is just b star, a star, a, b. And a star, a is always less than a squared times 1. So that means that since this is positive, this is less than, oops. So we see that indeed this is bounded. And we can safely extend it to the completion. So maybe I should have specified this is bounded on a Okay, so that's the first part of the statement. This gives us a operator. Next, we want to check that this is in fact a star representation. So we just need to check that it's an algebra map and it preserves the star. Okay, well, this is not so difficult to check on the dense subspace. So since that's true on the dense subspace, we get that this is additive. And then we need to check that multiplying elements together is the same as composition of operators. Again, this is not very difficult computation. Well, this is just AB C plus N phi. Of course, our multiplication is always associative, which means we get that this is a BC plus N phi, which is and since that's true for every C in A, we get that indeed pi of AB is pi A composed with pi of B. And then we need to show finally that it's star preserving. So that's maybe the slightly more tricky part, but not really. So we want to show that this is actually the adjoint of the operator pi 5a. So this is very misleading. It is not to be, yeah, okay. So, well, what is this? This is B plus N phi, A star B plus N phi, which is by definition B star A star B, which is A B star B, which gives us this. So we see that indeed the operator adjoint of this is the same as taking A star. So we've shown that this is a star homomorphism. And hence, indeed, we have a star representation. Okay, so this particular construction is called the Gelfand-Naimark-Segal representation associated to phi. So we can safely call it an honest representation now. Representation, but usually you'll just hear this called the GNS representation. Associated to this functional. So we saw that for any element A, normal element A, we can find some state, which in particular is a positive linear functional that takes norm equal to A on that element. So this is telling us that actually there's tons of these GNS representations. So we really have a rich representation theory for our C-star algebras. And we can define the direct sum of representations as follows. So we just take the direct sum of all the Hilbert spaces. And apply these pi lambdas coordinate wise. So we just take an element A to the direct sum of pi lambda of A. And clearly this is a representation. So I guess that requires a small amount of checking, but this is evidently a Hilbert space. And then you just need to check that since this is defined coordinate wise, indeed, it will be a star homomorphism. And an observation, this will be faithful as long as whenever we have a non-zero element in A, then some coordinate on some coordinate pi lambda of A is non-zero. Since that's enough to guarantee that this whole direct sum is non-zero. And from this, we're able to define what's called the universal representation. And this will be the direct sum of all GNS representations of all states. And we will end today with the Gelfand-Naimark theorem, which tells us that the universal representation of a C-star algebra is always faithful. So this essentially just follows from the fact that we know that we have enough states that at least one of them will be non-zero on any positive element A. So that means if we take some non-zero element A, then we saw that there exists a state, let's say phi A, such that phi A of A star A is equal to the norm of A star A, which is just the norm of A squared, which is non-zero since A is non-zero. And then by definition of our Hilbert space, we can, for example, just take pi phi of A, hit it on this element 1 A tilde plus n phi, or really any old element will do, but let's be a bit lazy. This is phi of A star A, and that's non-zero. So we see that this operator is indeed non-zero, and by this observation we had here, this implies then that the representation is faithful. So we had these two notions of C-star algebras, and it turns out that indeed, after all, they are the same. And I suppose I'm a few minutes early, but there's probably no sense in starting the next section just yet. So I will finish there.